More than 70% of our universe is composed of something so strange that it continues to baffle scientists. We still do not have a firm understanding of what it is. Dark energy is the term given to this mysterious thing, though it does not really describe what it is. It is one of the greatest mysteries remaining in our universe, and solving it could forever change our understanding of physics. Since the Big Bang, our universe has been expanding, with space itself stretching and pushing galaxies further away. For a long time, physicists believed that the energy that helped this expansion would eventually run out, causing the expansion to slow down. However, a Nobel Prize-winning discovery completely changed this idea. It showed that the expansion of the universe was not slowing down, but in fact accelerating. The scientific community began to wonder what could be causing this accelerated expansion. The mysterious force behind this was called dark energy, but giving it a name does not explain what really drives this acceleration. Just like dark matter, which makes up 25% of the universe and is also not fully understood. Dark energy seems to defy the laws of physics as we know them, behaving in ways that current models cannot explain. As the universe expands, more dark energy seems to appear, almost as if something arises from nothing, challenging our understanding. Scientists have proposed several ideas about what dark energy could be. Perhaps a new type of particle, a strange liquid, or even an unknown force. But so far, no explanation has fully accounted for this cosmic mystery. What we do know is that dark energy makes up about 70% of our universe, and its influence is deeply linked to the formation and evolution of it. At the beginning of the 20th century, astronomers discovered that the universe was expanding. They hoped that the gravitational force of all the matter in the universe would slow this expansion. However, over time, as we will see later, scientists discovered that the expansion of the universe was accelerating instead of slowing. One of the main ideas is that dark energy could be a property of space itself. According to Albert Einstein's theory of general relativity, space has its own energy, and as space expands, more of this energy is created. This energy could be responsible for the accelerated expansion of the universe. Another theory suggests that dark energy could be related to a new, unknown type of field or particle. Some scientists propose that it could be connected with the so-called cosmological constant, a term that Einstein originally introduced but later abandoned. The cosmological constant is a fixed energy density that fills space uniformly, causing the expansion of the universe to accelerate. A third possibility is that our understanding of gravity is incomplete. Dark energy might not be a separate force, but a sign that we need to revise our theories about how gravity works on a cosmic scale. Despite these theories, dark energy remains difficult to understand. What we do know is that it is not something that we can see or detect with traditional methods. It does not emit light or radiation, nor does it interact with matter in the usual way. Instead, we deduce its existence by the way it affects the expansion of the universe as it expands. Dark energy continues to separate galaxies at an ever-increasing rate. If dark energy continues to dominate the universe, it could continue to expand forever, becoming increasingly cold and empty as galaxies move further away from each other. In such a scenario, the stars would eventually go out, and the galaxies would become dark voids of space. Some scientists have even speculated that if the effects of dark energy become stronger over time, they could end up tearing apart galaxies, stars, and even atoms, a fate known as the Big Rip. However, this is just one of many possible outcomes, and much more research is needed to understand the true nature of dark energy and its impact on the cosmos. So dark energy remains physics' greatest cosmic secret. However, with all these great scientific minds around the world trying to figure out what it is, it may not be long before we finally discover something about this mysterious energy. The person who comes up with an idea about what it is could be the next Einstein. Music. When we look around us, everything we see and touch is made of matter. Small particles make up all the things we interact with. And over billions of years, these particles have come together to form galaxies and stars, all following the same physical laws and existing within the same space-time framework. But there was a time when the universe had nothing. So where did all this matter come from? Although it may seem that everything had to come from something, scientists also consider the possibility that everything came from nothing. But what does nothing really mean in science? To answer what was before the beginning of the universe, we must first understand exactly how the universe was created from what appears to be nothing. One of the main ideas of modern cosmology is the Big Bang Theory, which explains how our universe began and evolved. Imagine all the stars, planets, and galaxies compressed into an incredibly hot and dense point. Scientists believe that this is how everything began about 138 billion years ago. Since that moment, the universe has been expanding and cooling. Music. So how do we know this happened? The Big Bang Theory is supported by much evidence. A key piece is the cosmic microwave background radiation, which is like a glow from the early universe. This radiation gives us a picture of what the universe was like only 380,000 years after the Big Bang. Before that time, the universe was too hot and dense for us to see anything. This radiation was accidentally discovered in 1965 by Arno Penzias and Robert Wilson. Another important discovery is the redshift of galaxies, which shows that galaxies are moving away from us, proving that the universe continues to expand. This was first observed by Edwin Hubble in the 1920s. The further away a galaxy is, the faster it seems to move away from us, supporting the idea that the universe was once much smaller, hotter, and denser. The Big Bang Theory also explains why the universe has certain amounts of light elements, such as hydrogen, helium, and lithium. These elements were formed in the first minutes after the Big Bang, when the universe had cooled enough for protons and neutrons to combine and form nuclei. However, the Big Bang Theory also leaves us with big questions. For example, it does not explain what happened before the Big Bang or what is beyond the part of the universe that we can see. It also introduces cosmic inflation, the idea of a rapid expansion just after the Big Bang. This concept helps solve some problems of the theory and coincides with what we observe in the cosmic microwave background radiation. Before the discovery of the cosmic microwave background radiation, there was a popular idea called the steady-state theory. This theory suggested that the universe had no beginning or end and that it remained the same in general, even as it expanded constantly, creating new matter. Music. This theory was popular in the 1940s, but lost support when scientists discovered the cosmic microwave background radiation in 1965, which strongly supports the Big Bang Theory. Other ideas, such as the cyclic model, suggest that the universe goes through endless cycles of expansion and contraction. These theories are still being explored and developed, increasing our understanding of how the universe began after the Big Bang. The universe expanded and cooled at the beginning. It was a hot, dense soup of particles that, as it expanded, cooled, allowing particles to come together and form the first atoms. These atoms then formed the first stars and galaxies. The expansion of the universe continues today, with galaxies moving away from us in all directions. Let's think even further back. The first lasting particles, protons and neutrons, appeared about 1,000th of a second after the Big Bang. Before that, no material existed as we know it, but physics allows us to go back even further in time to processes that took place before any stable matter existed. This idea of how the universe originated from nothing also leads us to the concept of the Great Unification. One possible idea is that the universe was full of a hot mixture of particles, including quarks, which are the basic components of protons and neutrons. There was an almost equal amount of matter and antimatter. Each type of matter particle, such as a quark, has an antimatter counterpart that is almost identical, but with one key difference. When matter and antimatter meet, they destroy each other in an explosion of energy, which means that these particles are constantly created and destroyed. But where did these particles come from in the first place? If we think in terms of quantum field theory, it tells us that even a vacuum that we consider empty space is full of activity in the form of energy fluctuations. These fluctuations can cause particles to appear and disappear shortly thereafter. This may sound strange, but such particles have been seen in many experiments. The vacuum of space is full of particles that are constantly created and destroyed, apparently out of nowhere. However, this suggests that the quantum vacuum is actually something rather than nothing. Now let's ask ourselves where spacetime itself came from. To answer this, we have to go back to the beginning, to the Planck era, music Planck era. This period was so early in the history of the universe that our best theories of physics no longer work. It occurred only a tiny fraction of a second after the Big Bang. During this time, space and time were affected by quantum fluctuations. Physicists generally use quantum mechanics to understand tiny particles and general relativity for large cosmic scales. But to understand the Planck era, we need a complete theory of quantum gravity that combines both. We still don't have a perfect theory of quantum gravity, but ideas like string theory and loop quantum gravity suggest that ordinary space and time come from deeper, microscopic processes. What we experience as space and time is the result of quantum processes. At the moment, they don't make much sense to us because we're used to the large-scale world. Quantum fluctuations occur constantly, even in what we consider empty space. According to the Heisenberg uncertainty principle, pairs of particles and antiparticles can emerge from the vacuum, exist for a brief instant, and then destroy each other. This phenomenon is known as quantum foam, but quantum fluctuations alone do not explain the large scale and complexity of the universe. There is also dark energy, a mysterious force that fills all space and accelerates the expansion of the universe. Although we do not fully understand dark energy, it is believed to play a crucial role in the creation and evolution of the cosmos. So how did we get from quantum fluctuations and dark energy to the vast, structured universe we see today? The answer lies in inflation, a rapid expansion that occurred fractions of a second after the Big Bang. During this brief period, the universe expanded at an incredible rate, laying the foundation for the formation of galaxies, stars, and planets in the Planck era. Our usual understanding of space, time, and cause and effect falls apart. Despite this, all candidate theories of quantum gravity describe something physical that occurs during the Planck era as some quantum precursor to ordinary space and time. But where did that come from? Even if causality does not work in the usual way, it may still be possible to explain parts of the universe from the Planck era in terms of other parts. Unfortunately, our best physics still cannot give clear answers. Until we develop a theory that explains it all, we cannot give a definitive answer. The most we can confidently state is that physics has not yet found any confirmed case of something coming from nothing. Now that we understand the beginning of the universe, we will begin to explore what there was before nothing. None of the evidence from the cosmic microwave background radiation or quantum fluctuations tells us what existed before the Big Bang. The Big Bang theory explains that the universe began from an incredibly dense and hot point called a singularity. Think of a singularity as a point where everything we know about space and time breaks down. This singularity raises some big questions. If our usual laws of physics applied here, then what are the rules for understanding this? We have to look at the ideas of Albert Einstein. His theory of relativity changed our way of seeing the universe by connecting mass and time. According to his theory, time is not fixed, but it changes depending on the gravitational force of massive objects. He demonstrated that massive objects like the Earth can slow down time. Now, if mass slows down time, imagine what would happen with the singularity, which contains all the mass of the universe. It would stop time completely. Therefore, according to Einstein, the idea of what was before the Big Bang does not make much sense, since time itself did not exist. The cosmic microwave background radiation is a key test, as it comes from a time approximately 380,000 years after the Big Bang, when the universe was cooling and forming hydrogen atoms. Before this mark of 380,000 years, the universe passed through several stages, starting from the planetary era to the Great Inflationary Unification, passing through the eras of quarks and hadrons. In each stage, different particles and forces evolved into what we know today. When we talk about the universe on such a small scale, quantum mechanics replaces classical physics. This led scientists like Stephen Hawking to think about how quantum theory could be applied to the entire universe. This is where inflationary quantum cosmology comes into play. Unlike classical theories, which describe the singularity as a point with zero volume, quantum cosmology suggests that there is an element of uncertainty. This means that we cannot determine the exact moment when the universe was created and that particles can appear and disappear from what we call a vacuum. In physics, the vacuum is not completely empty, but a state without particles. According to the Heisenberg uncertainty principle, there is always some level of fluctuation, so a perfect vacuum with zero field values is impossible. The positive energy of stars and galaxies must be balanced by an equal amount of negative energy, such as gravity. If the total energy of the universe is zero, then it is possible that it comes from nothing. The idea that hundreds of billions of galaxies can arise from nothing seems incredible. However, the Einstein equation E = mc squared gives us some clues. According to this equation, all the positive energy of stars, galaxies, and other celestial bodies must be balanced by an equal amount of negative energy, which manifests as gravity in a closed universe or that will eventually collapse on itself. These positive and negative energies would perfectly cancel each other out, resulting in a net energy of zero for the universe as a whole. Stephen Hawking wondered how a universe with zero total energy could proceed from nothing. He suggested that the negative energy of gravity could balance the positive energy needed to create matter, making empty space stable. The physicist Alexander Venin expanded this idea, showing that a small vacuum full of energy, empty full of energy, could spontaneously appear from nothing and expand to become the universe we see today. This means that our universe could have started from a state of nothing, where time did not exist. So what was there before the Big Bang? The theories we have explored suggest that time itself began with the Big Bang, which makes the idea of before quite complicated. From singularities to quantum fluctuations, these ideas show how incredible and mysterious. The Big Bang theory explains how the universe expanded from an extremely hot and dense state, but it does not tell us what happened before that moment. According to the theory, time, space, matter, and energy began with the Big Bang. However, some scientists have ideas about what might have existed before the Big Bang. An interesting idea is the Great Rebound. This theory suggests that the universe goes through cycles of expansion and contraction. Another intriguing idea is the concept of a multiverse. This theory proposes that our universe is just one of many, each with its own set of physical laws. In this model, what existed before our Big Bang could have been another completely different universe. These ideas expand the limits of our current knowledge and explore speculative possibilities. They're based on advanced concepts of quantum physics and the still developing field of quantum gravity. Scientists are working to connect the dots between quantum mechanics and general relativity to better understand these possibilities. While these theories offer exciting visions of what might have existed before the Big Bang, they remain largely theoretical, highlighting the profound mystery of the origins of our universe. By looking back in time, we can explore the origins of each cosmic structure. Each discovery leads to another question. Where did this come from, and how did it form? These questions continue until we reach a point where the only honest answer is that we do not know, at least for what we understand. Then we are faced with the fundamental questions. How did all this come about? After the Big Bang, the universe continued to expand and cool. At first, it was just a mixture of tiny particles, but as they cooled, these particles joined together to form the first atoms, mainly hydrogen and helium. The life we see today is possible thanks to complex molecules that evolved from the simple atoms listed in the periodic table. These atoms are the fundamental components of all ordinary matter in our universe. They were not there from the beginning of the universe, but were formed through cycles of stars that are born, live, and die. Each cycle of stellar life contributed to the nuclear reactions that produced these atoms, which were then recycled into new generations of stars. Without this continuous process, the creation of planets, and the complex chemistry needed for life would not have been possible. To understand how the stars and galaxies that we see today came to exist, some key factors must occur. First, gravity plays a very important role, as it attracts smaller groups of stars and galaxies to form the large galaxies we observe, triggering new rounds of starbirth. For gravity to do its job, there must be enough mass already clustered. This is where dark matter comes into play. Early in the history of the universe, dark matter forms halos that help prevent newly formed stars from scattering their material back into space. In addition, the right mix of matter, including atoms, dark matter, and radiation, is crucial. This mixture not only produced the cosmic microwave background, a kind of residual glow from the Big Bang, but also created the light elements during the hot and dense state of the early universe. The growth of galaxies and star clusters depends on small initial differences in density, often called seed fluctuations, which needed to grow under the influence of gravity. Finally, there had to be processes that initially created these density variations, dark matter, and the first batches of ordinary matter. To understand how our universe emerged from the chaos of the Big Bang, we have to take into account some critical conditions from the beginning. The laws of physics, the structure of space itself, and the essence of matter and energy were not simply there. They had to arise in some way. We are guaranteed to find an identical copy of our entire universe, as well as countless multiple universes, which raises the question, are there other versions of you in a parallel universe? Variations of reality in which things are similar to those here, but different, now considered a real possibility? You probably won't be surprised that studying parallel universes was once considered crazy in the scientific world. It even drove away the people who decided to dedicate themselves to it. But now theoretical physicists have realized that parallel universes are possible, at least mathematically. One of the reasons for this comes from the strange world of quantum physics. The most important thing to remember about quantum mechanics is that it is really strange. It is the study of subatomic particles, which are the building blocks of everything in the universe. Quantum mechanics tells us that these particles can behave as particles and as waves at the same time. This dual nature divides our reality, creating multiple different universes. The idea is that when you measure a particle that exists in two places at the same time and find it in one place, there's another version of you in a different world that finds it in the other place. Both worlds are equally real, so the quantum multiverse is not separated from us by distance. It is not a distant place. It is effectively right here in space, but the complexity of quantum dynamics prevents these different branches from interacting with each other, whether you like it or not. The idea that we live in a multiverse is now the prevailing scientific view. Another theory is based on mathematical inevitability. If our universe is made of a finite amount of simple matter, then it follows that other universes are made in a very similar way. Just as a house is built from basic blocks like bricks, everything in our world is made of elementary particles. If a random process organizes these particles in a finite space, there are countless ways this could happen. If this process is repeated in an infinite number of other spaces, we are destined to find an identical copy of our universe, as well as countless variations in which things are similar but slightly different. There could even be a version of me out there that is identical to me in every way, including the feeling that it is me. Another theory called inflation explains how the universe expanded rapidly in the first fraction of a second after the Big Bang. This rapid expansion created bubbles or pockets of spacetime where other universes could have formed. If this theory is correct, then these pocket universes could have their own laws of physics, which means there could be another you in those universes who can walk through walls or fly through space. According to quantum theory, with every decision you make, a new version of you and a new universe is created. Every decision you make, for example, every time you flip a coin and say heads or tails, the universe splits into two worlds based on the outcome. Our experience of this is like walking through a garden with forking paths. When we come to a fork, we choose one path or the other, heads or tails, but both paths exist at the same time. We only experience one of them. There are countless universes out there, ours being just one. Then there is the mosaic model, which suggests that there's an almost identical copy of our universe somewhere else. In this type of parallel universe, there's another you who is very similar, only with small differences. We are destined to find infinite variations where things are like here, but still different. For example, in one universe, the asteroid that wiped out the dinosaurs did not impact the Earth. So there are no humans, only dinosaurs walking through Winchester today. All these ideas suggest that there are multiple strange and wonderful universes, and although we cannot see the entirety of our own universe, scientists believe they may be getting closer to understanding these possibilities. The truth often goes through three stages. First, it is ridiculed, then strongly rejected, and finally it becomes evident. Perhaps we are now reaching that stage of evidence. A mysterious feature within the cosmic microwave background is the cold spot, a large area with lower than average temperatures. An interesting theory about the cold spot is that it could be a cosmic bruise left when our universe brushed against another universe. This idea supports the concept of a multiverse in which multiple universes exist and sometimes interact. In 2007, scientist Laura Massini-Holton discovered something unusual. She found evidence that our universe collided with another universe. Scientist Laura Massini-Holton discovered something unusual. She found evidence that appeared to show two universes crossing. The detection of a cold spot was one of the signatures she predicted when tracking the quantum entanglement of our universe with other surviving universes. She suggested that this cold spot may have slowed expansion in that part of our universe, which would have led to the colder temperatures that we see today. Recently, there's been a major breakthrough in the theory of inflation, which predicted that if the universe expanded rapidly, it would send waves through space. These waves are known as gravitational waves. We had not detected anything like it until 2015, when two experiments managed to detect gravitational waves coming from the fusion of two black holes. This detection makes it more likely that we can detect gravitational waves from inflation. But why should we care if multiple universes exist? Well, it relates to the old question of what our universe expands into. If other universes exist, perhaps ours expands while the neighbors are contracting. This could give us more information about our own universe, especially about how it might end. Over time, our universe could expand until neighboring universes had their own Big Bang and began to expand towards us, causing our universe to contract and possibly end in a great collapse instead of Big Bang. Over time, these ideas have led to investigations into anomalies that might resemble the theory of cosmic inflation, according to which everything in the universe should be evenly distributed across the sky, but anomalies such as the cold spot of the cosmic microwave background challenge this idea, hinting that the history of our universe could be more complex than we thought. British physicist Brian Cox has debated how the idea of multiple universes fits into a concept called eternal inflation. According to this theory, our universe is just one bubble in a vast spacetime filled with other bubbles. These bubble universes are constantly being formed. The process begins when a certain region of space stops expanding rapidly. However, not all regions of space stop expanding at the same time. Some areas continue to expand, leading to the continuous creation of new universes. Each of these universes may have its own physical laws, which could be very different from those we know. To imagine this idea, think of a vast library with countless books. Each book represents a different universe. If the library has an infinite number of books, then all possibilities exist in one of them. In one book, gravity could be weaker, allowing creatures to grow larger and buildings to reach much greater heights. In another book, the speed of light could be slower, changing the behavior of light and energy. But these differences between universes are not only about physical laws. They could include completely different stories and evolutions. Imagine a universe in which dinosaurs never became extinct and became the dominant intelligent species, or think of a universe in which the basic elements of matter are different, giving rise to planets and stars made of dark matter instead of the substances we know. When we look at the night sky, we see stars, planets, and galaxies scattered across the vastness of space, But everything we can see with our eyes, telescopes, and other instruments represents only a small fraction of the entire universe. It is estimated that the universe we can observe is only 5%. The other 95% is something we cannot observe directly. This 95% is something we have not yet discovered. This hidden majority is made up of dark matter and dark energy, two mysterious components that play a crucial role in the structure of the universe. But why can't we see this 95%? And what does it mean for our understanding of the cosmos? To understand what we cannot see, let's first discuss what we can see. The observable universe includes all matter that emits, reflects, or interacts with light or other forms of electromagnetic radiation. This includes stars, planets, galaxies, nebulae, and even cosmic background radiation, which is the residual glow from the Big Bang. When astronomers use telescopes to observe the universe, they rely on light to gather information. For example, when you look at the night sky, you are seeing light that has traveled through space for years, even millions of years before reaching your eyes. This light carries information about the objects from which it comes, allowing scientists to study their composition, distance, movement, and much more. However, this visible matter that forms stars, planets, and galaxies represents only a small part of the total content of the universe. The remaining 95% of the universe is made up of two undetected components, dark matter and dark energy. Dark matter makes up between 25 and 27% of the universe, and we can only detect it through its gravitational effects on visible matter. Dark matter acts as a cosmic skeleton that guides the structure and formation of galaxies. The most difficult component to understand is dark energy, which makes up approximately 68% of the universe. This mysterious force causes the universe to expand at an ever-increasing rate. Together, these components make up the fabric of the cosmos and influence everything from the smallest particles to the largest galactic structures. We still don't know exactly what dark matter and dark energy are, but we are quite sure they exist. So what do we know? Unlike the matter we are familiar with, dark matter does not emit, absorb, or reflect light, making it completely invisible to us. We cannot see it with telescopes or detect it using any of our traditional methods. So how do we know it exists? The existence of dark matter was first proposed when astronomers observed that galaxies rotated much faster than they should, according to the amount of visible matter they contain. According to the laws of physics, if a galaxy contains only the matter we can see, its outer edges should rotate more slowly than its inner regions. However, observations show that the outer parts of galaxies moved as fast as the inner parts, suggesting that something else invisible was providing an additional gravitational pull. This invisible substance is what we now call dark matter. Although we cannot see dark matter directly, we can observe its effects on visible matter. For example, when light from distant galaxies passes through a region of space with a lot of dark matter, the light is curved, a phenomenon known as gravitational lensing. This curvature effect allows astronomers to create a map of the distribution of dark matter in the universe, even if they cannot see it directly. But what is dark matter comprised of? This is one of the biggest unanswered questions in modern physics. Some theories suggest that dark matter could be made of particles that do not interact with light or other electromagnetic forces, so they remain invisible. These particles could interact uniquely through gravity, so we can detect the gravitational effects of dark matter, but not the matter itself. Even more mysterious than dark matter is dark energy, which constitutes about 68% of the universe. Dark energy is believed to be responsible for the accelerated expansion of the universe. For most of the 20th century, scientists thought that the expansion of the universe, which began with the Big Bang, would gradually slow down over time due to the gravitational attraction of all the matter in the universe. However, when astronomers observed distant supernovas, they discovered that these objects were farther away than expected, indicating that the expansion of the universe was accelerating. This unexpected acceleration led to the idea that some unknown force, now called dark energy, is driving expansion. But what is dark energy? Is it like dark matter? We don't know exactly what it is. Some theories suggest that dark energy could be a property of space itself, while others propose that it could be related to a new field or particle. Scientists are quite sure that they exist. Why? Because dark matter is essential for galaxies to form. When scientists study the structure of the universe, they realize that the amount of visible matter is not enough to explain how galaxies are held together. The gravity of visible matter alone is not strong enough to form galaxies or complex systems without dark matter. The stars would probably be scattered randomly instead of clustering into the galaxies we see. This suggests that dark matter acts as a glue that keeps everything together. Although dark matter is invisible, it can be detected indirectly in areas with a lot of it, since the light that passes nearby curves, creating a lens effect. This curvature of light reveals where dark matter is located based on its gravitational pull. So what is not dark matter? First, it is not ordinary matter without stars, since normal matter emits detectable particles that make it visible. If dark matter were just ordinary matter, we would have already seen it. Nor is it antimatter, since when antimatter comes into contact with normal matter, it emits gamma rays. If dark matter were antimatter, we would detect these rays, but we do not. Dark matter is also not composed of black holes. Black holes are dense objects with a strong influence on their environment, while dark matter appears to be scattered throughout space. The gravitational effects of black holes are different from those we observe. With dark matter, scientists continue to test different ideas and conduct experiments to find out what it really is. Even with precise tools, such as the Planck spacecraft of the European Space Agency, we can only detect less than 5% of the total observable universe. For years, scientists have tried to solve the mystery of dark matter, but so far we only know that it exists because of its gravitational effects on visible matter. British physicist Brian Cox suggests that dark matter could be composed of particles that we have not yet discovered. But how can we actually find it? Scientists are looking for this mysterious substance using the world's largest physics experiment at the Large Hadron Collider in Switzerland. Instead of just trying to detect dark matter, they're trying to create it from scratch. To do this, they collide known particles at extremely high speeds, creating enormous amounts of energy. This energy could produce dark matter particles. When protons collide, they usually create new particles, but most of them are light. Occasionally, these collisions create much heavier particles, and those are the ones that scientists hope to find. Scientists believe they're getting closer to discovering what it is made of. One of the main candidates for dark matter are weakly interacting massive particles. They interact very weakly with normal matter, making them incredibly difficult to detect. Underground detectors are designed to capture these interactions and provide clues about dark matter. An interesting test comes from gravitational lensing. This happens when light from distant objects, such as galaxies or quasars, curves around a massive object, such as a cluster of galaxies. Due to gravity, the amount of curvature tells us that there is dark matter that adds to the overall gravitational pull. Astronomers also play an important role in the search for dark matter by studying the night sky. They observe how galaxies and clusters of galaxies move. The behavior of these large structures suggests that there is more mass present than we can see, and that is where dark matter comes in. For example, when astronomers observe the speed at which stars orbit the center of galaxies, they realize that there must be additional invisible mass, probably dark matter that holds everything together. Although we have not yet directly found dark matter, each experiment brings us closer to understanding this mysterious part of the universe. Dark energy is even more mysterious than dark matter. It is a type of energy that we cannot detect or measure directly, but we can observe its effects. Unlike dark matter, which clusters due to gravity, dark energy is uniformly distributed throughout space. In 1929, the astronomer Edwin Hubble made a revolutionary discovery. He observed that light from distant galaxies shifts towards the red end of the spectrum as it travels through space. This effect, known as redshift, revealed something surprising. Hubble discovered that the farther away a galaxy is the more its light shifts towards the red, while closer galaxies show less redshift. He deduced that this occurs because the universe is expanding. As the light stretches, it shifts towards the red part of the spectrum, which demonstrates that space itself is getting bigger. Recent discoveries have taken Hubble's findings even further. The universe is not only expanding, but also accelerating. Scientists used to think that gravity would eventually slow down this expansion or even reverse it, but now they know that dark energy is driving this rapid expansion, pushing the universe faster and faster. Space does not change as it expands, but new space is constantly being created everywhere. Galaxies are held together by gravity, so we don't feel this expansion in our daily lives, but we can see how it happens throughout the universe. Wherever there is empty space, more is being created every second. So what exactly is dark energy? It seems to be a type of energy in empty space that is stronger than anything else we know and continues to grow. Empty space contains more energy than everything else in the known universe combined. This mysterious force is separating the galaxies and causing the universe to expand even faster. Dark energy remains one of the greatest mysteries of cosmology. Although we cannot detect or measure it directly, its impact on the universe is clear now. Undoubtedly, we know the reason why we cannot see 95% of the universe is that dark matter and dark energy do not interact with light or other forms of electromagnetic radiation in the same way that ordinary matter does. Instead, we infer its existence based on its effects on the visible universe. In the case of dark matter, this includes its gravitational influence on galaxies and the curvature of light. In the case of dark energy, it is the observation that the expansion of the universe is accelerating instead of slowing. In a sense, the visible universe is just the tip of an iceberg. The stars, planets, and galaxies that we can see are like the visible peaks above the waterline, while the vast majority of the universe lies hidden beneath the surface, invisible and mysterious. Look closely at this picture. This is Eugene Cernan, the last astronaut of the Apollo program to walk on the moon. But something seems strange until you realize the night sky looks completely empty without any stars. In fact, all the photos taken during the Apollo missions show a starless sky, even though the universe is full of trillions of stars. The Apollo astronauts said they couldn't see a single star from the moon. This lack of stars has fueled conspiracy theories, and some people claim that the moon landing was fake, but the real explanation is much more interesting and profound than any conspiracy theory. The reason why the stars do not appear in the photos taken on the moon is mainly due to the camera's settings. When astronauts take photos on the moon, they usually capture the luminous surface of the moon. The surface of the moon is illuminated by the sun, and to capture this brightness correctly, the camera uses a fast shutter speed and a low ISO setting. But even so, when we see the night sky from Earth, we mainly see darkness. Why does space look so empty? This problem was first raised by the German astronomer Johannes Kepler in 1610. Our galaxy, the Milky Way, is huge, with an estimated between 100,000 and 400,000 million stars. In addition, the observable universe has trillions of galaxies, each with trillions of stars. Careful studies suggest that the sky should be as bright as the surface of the sun. But when we look up at night, we mainly see darkness. This enigma, known as Olber's paradox, took almost 300 years to resolve. With so many stars in all directions, astronomers wondered why the entire sky is not bright and full of light. Olber's paradox is based on the steady-state theory. Imagine a universe in which everything has always remained the same and always will. The position of the stars, the galaxies, everything. This was the main idea behind a steady-state theory, which used to be the most popular explanation of the universe. It said that the universe was infinite, without beginning or end, uniform in all directions, and that it was not expanding. With this theory in mind, astronomers faced a big question. If the universe is full of stars and has always existed, why is the night sky dark? According to the steady-state theory, even the light from the most distant stars should have already reached us, filling the sky with its glow. One of the first ideas was that perhaps the stars are too far away to affect our night sky, but this did not make sense with the steady-state model. If the universe is infinitely old, there has been plenty of time for light from any star to reach Earth, even from the farthest parts of the universe. This light should fill the sky without leaving dark areas. Johannes Kepler had a different idea to solve the paradox that went against the steady-state theory. He suggested that the universe is not infinite, but he thought that the stars only extend to a certain limit, and beyond there is only empty space. This idea was interesting, but it raised new questions. How far does this space with stars go, and what is beyond that limit? Kepler's idea, the limited universe, had its own problems. If the universe had a limit, the combined gravity of all the stars and planets could pull everything back and cause the universe to collapse. Due to these challenges, most astronomers continued to believe that the universe was infinite, which meant that the paradox and the steady-state theory remained unresolved for almost 200 years. Then, a famous German astronomer named Heinrich Olbers again drew attention to this old question. Why is the night sky dark and looks empty? Since then, Olbers' name has become closely linked to the paradox. At that time, people still believed that the universe was immutable. Olbers suggested a simple idea. If the universe is infinite, it would be full of dust and rocks, and these particles could block the light from distant stars, making them appear dimmer to us. This cosmic dust and these rocks would absorb and block the light from the stars as they move through space. Nowadays, many people still think of space as Oba did, like clouds blocking sunlight and hiding the sky. Like clouds, cosmic dust and rocks can obscure the light of the stars. But Ola's explanation was not the whole story. Over time, the dust and rocks that blocked the light would heat up and begin to glow on their own. This means the universe would still be full of light, just as before. The dust and rocks would only temporarily block the light from the stars before releasing it again. So the total amount of light reaching us would still be the same. So, what really solves this mystery? It took us another 100 years to find the real answer. In 1929, Edwin Hubble used his powerful telescope hoping to find evidence that the universe was shrinking, which would support the idea of a limited universe, as Kepler suggested. But instead, Hubble discovered that the galaxies were moving away from us, and the further away a galaxy was, the faster it seemed to move. This showed that the universe was not staying the same or collapsing, but actually expanding. This discovery led to a new question. What does an expanding universe mean for its origin? Scientists now believe that the universe began as something incredibly small and dense, which then expanded rapidly in a process called cosmic inflation. As it expanded, it cooled, and eventually stars and galaxies began to form. This understanding led to what we now call the Big Bang Theory. Scientists think that everything started about 138 billion years ago, and currently, it is our best explanation of how the universe began. Today, most scientists agree that the universe is about 138 billion years old. When we look at light that is 138 billion years old, we don't see stars, not because the light hasn't reached us, but because we are looking back to a time before stars existed. The further we look into space, the further back in time we see, until we reach what looks like the edge of the universe. This is not a real edge, but the oldest light we can see, known as the cosmic microwave background, is the afterglow of the Big Bang. When we use telescopes to look beyond the first stars, we see this special type of light. It is not light from the stars, but residual light from the Big Bang. It forms a background beyond where the stars are. However, the Big Bang Theory raises a new question. It suggests that the universe used to be much brighter, especially during a time called the recombination era. Back then, the entire sky would have been as bright as the sun because the universe was very hot. This means that the Big Bang background, known as cosmic background radiation, should be very bright. According to Ola's paradox, this bright background should make it difficult for us to see any faint stars in the night sky. Since the Big Bang occurred 138 billion years ago, the universe has followed three main rules as it grows and changes. First, in the beginning, The universe was incredibly small, very dense, and extremely hot. Second, only a fraction of a second after it began, the universe began to expand and cool. Third, and this is really important, the universe will continue to expand and cool. Astronomers believe that this will continue until the universe cools so much that all the heat disappears, a scenario they call the thermal death of the universe, also known as the Great Freeze. In this future scenario, the universe will have expanded so much that it will cool completely and all thermal energy will disappear. These rules show us that our universe has been getting bigger for the last 138 billion years. When the universe began, it was full of very bright and hot light. As the universe expanded, this light stretched, becoming longer wavelengths, making it cooler and dimmer. This stretching of light is known as the redshift effect. That is why cosmic background radiation is not extremely bright. Thanks to the discovery of redshift and cosmic background radiation, we now know that the Big Bang and the expanding universe solve Euler's paradox. The universe began at a single point and expanded rapidly during the Big Bang, and over billions of years it has cooled because the universe is not infinitely old. There's a limit to how far we can see into space. The redshift effect also makes the light from distant objects appear dimmer. These factors together explain why the night sky looks dark today. The darkness of the night sky shows us that the universe is always changing and growing. Seeing a dark sky instead of a bright one tells us that the universe began with the Big Bang and has been expanding since. The night sky is a quiet reminder of how the universe began as a very hot and dense place. This understanding not only solves Euler's paradox, but also helps us appreciate how incredible and complex the universe really is, with 8 planets and numerous celestial objects. Our own solar system is one of the countless planetary systems scattered throughout the Milky Way. In addition, there are more than 1 million smaller objects, such as asteroids, comets, and meteorites. The planet farthest from the Sun that we know of is Neptune, which orbits about 30 astronomical units away, about 4 light hours, but Neptune's orbit only covers a small part of our solar system. The farthest object discovered so far in our solar system is called Far, Far Out, which is 132 astronomical units, or 18 light hours from the Sun. Even so, this object is still nowhere near the edge of the Oort cloud, which begins about 2,000 astronomical units from the Sun. The outer limit of the cloud could extend up to 60 billion astronomical units, or outer limit of the Oort cloud, which could extend up to 60,000 astronomical units, or approximately 1 light year. These limits are set by the gravitational pull of the Sun, and beyond is interstellar space. As we move away, we find over 50 stars less than 20 light years from the Sun. These stars vary greatly, from cold brown dwarfs to bright stars like Sirius and Betelgeuse. Some of these stars have their own planetary systems, and some of those planets may be capable of harboring life. For example, G832c, located 161 light years from the Sun, is more similar to Earth than any other known planet. The average temperature in Gle 83.2s is about 153 Kelvin, or about 20 degrees Celsius below zero, and it takes only 36 Earth days to complete an orbit around its star. In astronomical terms, the distance between us and GLE 832 is relatively small. However, if a space probe were to leave our solar system traveling at about 17 kilometers per second, it would take about 300,000 years to reach 832c. With our current technology, it is impossible to design a spacecraft that can make such a long journey. Our solar system, along with the nearby stars, is part of the Orion Arm, which in turn is part of the Milky Way. It is estimated that the Milky Way contains about 400 billion stars and potentially over 1 trillion exoplanets. Today, we estimate that the Milky Way is about 100,000 light years in diameter, with an outer halo that could be twice that size. The main disk of the Milky Way is about 1,000 light years thick, and there is a central bulge about 3,000 light years thick. The Milky Way is part of a group of over 50 galaxies called the Local Group. This group of galaxies extends over an area of space about 10 million light-years in diameter. The largest galaxies in the local group are the Andromeda Galaxy, the Triangulum Galaxy, and the Milky Way. The total mass of the local group could be up to 3 trillion times the mass of the Sun, with the Milky Way and Andromeda comprising most of that mass. Andromeda, which is about 25 million light-years from Earth, is the closest large galaxy to us, apart from the smaller, or dwarf, galaxies that are even closer. The local group is part of the Virgo supercluster, a massive structure containing more than 30,000 galaxies. This supercluster extends over a space about 150 million light-years wide and has a total mass equivalent to approximately 1 quadrillion suns. The Virgo supercluster is somewhat flattened, with approximately 60% of its galaxies forming a flat sheet about 10 million light-years thick. Although this may seem enormous, it is actually small compared to the largest structures in the universe. If we zoom out further, we can see a giant supercluster of galaxies called Laniakea, which is about 520 million light-years in diameter. Laniakea includes several superclusters of galaxies, including the Virgo supercluster and an area known as the Great Attractor. The total mass of Laniakea is approximately 100 quadrillion times the mass of the Sun. The Great Attractor, located about 250 million light-years away, is the gravitational center of nearby objects, but cannot be directly observed from Earth because the Milky Way obscures it, so the nature of the Great Attractor remains a mystery. Laniakea is part of the large-scale structure of the universe, a complex system of galactic filaments, walls, and vast voids of empty space in the cosmos. Some of these structures are incredibly massive. For example, the Great Wall of Hercules Corona Borealis extends to the staggering distance of 10 billion light-years. Since its discovery in 2013, this superstructure has been considered the largest known structure in the universe. It probably contains millions of galaxies with an uncountable number of stars. The existence of such a colossal structure is a mystery to scientists, as our current understanding of the evolution of the universe suggests that something so large should not yet have formed. Despite its enormous size, this wall is still only a small part of the observable universe. According to current cosmological theories, space and the universe are constantly expanding, and the rate of expansion depends on the distance between objects. The further away an object is, the faster the distance between it and the observer increases. This expansion is not limited by the speed of light, as it is space itself that is expanding. As a result, at a certain distance, two objects become unobservable to each other. Observations of the cosmic microwave background suggest that the observable universe is a sphere with a diameter of approximately 93 billion light-years. According to the theory of relativity, we can only see and interact with objects within this sphere. This spherical area in space is called the metagalaxy and could represent the entire universe or just a small part of it. Hypothetically, there could be unknown structures beyond the visible limits of space. These are known as extraterrestrial metagalactic objects. However, unfortunately, we cannot study them with current scientific methods. Some astronomical bodies on the edge of the visible universe appear to move in ways that do not match expectations based on the data we have. These unusual movements could suggest the presence of massive structures beyond the limits of the metagalaxy, whose gravitational pull affects nearby objects. There are many hypotheses about what lies beyond the metagalaxy, but most are more philosophical than scientific. For example, some believe that time and space, as we know them, do not exist beyond the limits of the universe. The physical laws with which we are familiar may not apply there, and concepts such as matter and energy may be meaningless. This idea suggests that the metagalaxy is only part of an even more complex and larger structure in space with dimensions and properties beyond our understanding. It is possible that this structure exists in a multidimensional space or operates according to physical principles that we have not yet discovered, which would make the metagalaxy only a small part of something much more incredible. According to some interpretations of the anthropic principle, There could be other universes beyond the limits of the observable universe. In these universes, fundamental constants, such as the speed of light or the charge of an electron, could be completely different. This idea is supported by the concept of a multiverse that can be imagined as a foam with many bubbles, each separated by thin walls. These walls are penetrable, which means that each universe is its own separate space with its own physical laws. These laws could be quite different from the ones we know. The most radical ideas even suggest that our world may lack any objective reality. According to these theories, the universe could be a simulation, like an incredibly advanced virtual reality. These ideas usually propose that there are superior beings or super civilizations beyond the reality that we know, beings whose level of advance is far above ours, and whose objectives and capacities are impossible for us to understand. Of course, it is almost impossible to demonstrate or disprove these theories. The distances in space are so vast that they are almost impossible to imagine and can even seem terrifying, since they seem infinite from our perspective. What we do know is that the universe is expanding, and if this continues, there will be a point where spatial objects will disappear one after another. Beyond the event horizon, first the galaxies, then the stars and the universe will end up sinking into eternal darkness, but by then there may be no one left to witness it. Our yellow dwarf star, the Sun, provides us with light and heat every day, is located on the outskirts of the Via Lactea and orbits around the center of the galaxy following a trajectory known as a correlation circle. This means that the movement of the Sun is synchronized with the rotation of the spiral arms of the galaxy, where new stars are born. Thanks to this alignment, the solar system rarely enters these arms, which keeps us safe from the harmful explosions of supernovas and the intense heat of active stars. The distance of the orbit of the Sun to the center of the Via Lactea is also important. If the Sun were closer to the center, the abundance of heavy elements would have caused the planets to form too large and massive. In addition, the intense radiation from the galactic nucleus would have made it almost impossible for life to develop on these planets. On the other hand, if the Sun were further from the center, the lack of diverse elements would mean that rocky planets like the Earth, rich in diverse chemical compounds, would not have formed. Instead, the Sun would probably be surrounded only by gas giants or icy worlds. There are also interesting coincidences within our solar system. For example, Earth is located at the right distance from the Sun and follows a stable, almost circular orbit. If the Earth's orbit were only 5% closer or further from the Sun, our planet would be frozen or covered by a thick layer of water vapor. In either of the two cases, advanced life as we know it would not exist. The Sun itself has several critical characteristics. It is not too hot or too cold and has a long useful life. Although the hottest stars create wide habitable zones, they do not last long enough and their radiation is too intense. The coldest stars, like red dwarfs, have narrow habitable zones, often too close to the star, which can cause planets to become tidally locked, which means that one side of the planet is always facing the star, causing extreme temperature differences between the two sides. Some might argue that life adapted to the conditions of the Earth rather than the Earth being perfectly suited for life. While this is a reasonable point, there are deeper aspects of the universe that challenge this idea. For example, stable orbits of celestial bodies are only possible in a three-dimensional space. In other dimensions, the orbits of electrons within atoms would become unstable, causing atoms to collapse or separate, which means that atoms and, by extension, matter could not exist in a universe with more than 3 dimensions. It would only contain radiation and free particles. Another important point is the existence of fundamental constants on which all modern physics is based, such as the speed of light, the gravitational constant, the Planck constant, and the masses of the electron and the proton. These values have been determined by experiments, and, although they are considered independent of each other, science has not yet explained why they have the specific values they do. For example, the mass of a proton is slightly greater than that of an electron, and this small difference is crucial, since without it the proton-electron system would not exist. Hydrogen atoms would become neutrons, and there would be no hydrogen in the universe. Without hydrogen, the stars would not form, nor would the heavier elements exist. If the values of the strong nuclear force were even slightly different from what they are today, the nuclear reactions that power the stars would not be possible. If the gravitational constant were stronger, the stars would compress too much, which would cause the formation of many large and hot stars with very short lives. After most of the matter in the universe is burned, would end up trapped in black holes and neutron stars, leaving little material to form planets, moons, and other spatial objects. On the other hand, if the gravitational constant were weaker, the interstellar gas would not compress enough for nuclear reactions to be self-sustaining. In that case, the stars would not ignite, and the universe would be full of giant brown dwarfs. Any change in the electromagnetic force would make chemical reactions and the formation of complex compounds almost impossible. If the strong force were stronger, there would be no elements heavier than boron, because their nucleus would disintegrate due to the repulsion between protons. The formation of heavy elements in the universe depends on several factors that work perfectly together. For example, a special state of carbon, known as carbon resonance, allows helium to fuse with carbon. This process is crucial for the creation of heavy elements and their distribution throughout the universe. Carbon resonance is also the reason why stars become supernovas, shedding their outer layers. The atoms created inside these stars are scattered through space, eventually forming planets, moons, asteroids, and other celestial bodies. In addition, carbon is essential for life, since it can form long and complex chains that are the basis of a wide range of chemical compounds. Life as we know it depends on organic compounds that would not exist without carbon. So it is clear that the universe, the life in it, and intelligent beings like us exist thanks to a series of remarkable and not so obvious coincidences. The theories that explain this often go beyond physics and delve into philosophy. One of these theories is the anthropic principle. Although the term was coined in 1973, the ideas behind it were expressed much earlier. For example, the Soviet scientist Grigory Aydin wrote in 1958 that what we observe in the universe is not random, but is a part that has been adapted for the development of life thanks to its special structure. This perspective is known as the weak anthropic principle. Later, the strong anthropic principle was introduced, which suggests that the universe must have certain properties that allow intelligent life to evolve. In other words, an observer is necessary for the universe to exist. This idea is related to quantum physics, where the presence of an observer significantly affects the behavior of particles. That is why an observer is essential in any quantum experiment. The laws of the universe are what they are because we can only exist in a universe with these specific laws. The anthropic principle suggests that there could be other universes or different parts of our own universe that follow different physical laws. However, either we cannot observe those places, or those hypothetical worlds cannot exist without someone observing them. This idea can lead to theories such as the multiverse, in which the basic physical constants may change over time, but all the observations in the parts of the universe that we can see show that these fundamental values remain consistent. The concept of multiverse is hard to describe within the limits of science in general. The anthropic principle goes beyond the scientific vision of the world and leans more towards metaphysical thought. As Len, the character of Stannis, once said, it is an attempt to explain the unknown with the unknown. The anthropic principle also seems to conflict with the principle of mediocrity. The principle of mediocrity states that the part of space that we can observe is nothing special and that there are many similar regions in the universe. For example, the Via Lactea does not have any particularly unique characteristic, and its position in the universe is not especially remarkable compared with the billions of other galaxies. In addition, there is the principle of homogeneity of space, widely accepted in modern physics, which means that the natural laws are the same throughout space. This idea is supported by countless observations of the universe around us. Human beings have always been curious about these great questions. Are we alone in the universe? Is the Earth unique? Are there other planets similar to the Earth in the Via Lactea? Science has not yet been able to give clear answers to these questions, but if it could, it would probably lead to a complete revolution in our understanding of the world, taking our knowledge to a completely new level. Until then, everyone is free to form their own opinion. When we think about how huge the universe is, it is obvious to wonder if we really matter, if we are special, or if there are other forms of life out there in the cosmos. This leads us to the question of whether the universe was created specifically for us. This idea is related to the anthropic principle that we have discussed. It suggests that the basic laws and constants of the universe seem to be perfectly configured for life, especially intelligent life like that of humans, for example. The exact force of gravity, electromagnetic forces, and how atoms work are crucial for life. Even small changes in these constants could make life, as we know it, impossible. So, does the fact that the universe is so precisely tuned mean that it was designed just for us? Some people think that the conditions that allow life are too perfect to be a coincidence, suggesting that there could be a purpose behind it. On the other hand, others believe that this fine-tuning is only the result of natural processes and chance. They argue that in a universe as vast as ours, it is not surprising that at least one planet like Earth has ended up with the right conditions for life. The multiverse theory adds another perspective. It suggests that our universe could be just one of many, each with its own set of physical laws and constants. In this multiverse, only a few universes could have the right conditions for life. If this theory is true, our universe is not particularly unique. It is just one of the few where life could arise, which makes the idea of fine-tuning less remarkable. The search for life beyond Earth also affects this debate. Finding life elsewhere, whether microbes on Mars, in the oceans of moons like Europa and Enceladus, or on distant exoplanets, would suggest that life is not unique to Earth, but could exist wherever conditions are right. Such discoveries could change our way of thinking about the rarity of life in the universe beyond science. Philosophical visions also influence how we understand the universe. Some people find comfort in believing that the universe has a specific purpose, while others see beauty in its randomness and its infinite possibilities. Regardless of whether the universe has a purpose, our natural curiosity and our desire to explore are fundamental human traits. Asking ourselves these big questions not only drives scientific progress, but also helps us to better understand the cosmos. Science shows us a universe that is vast and seemingly indifferent, which can make us feel small, but some argue that we could still have a special place in the cosmos because the laws of physics are so perfectly tuned to make life possible. For example, the exact force of the electromagnetic force is crucial for stars to produce carbon, which is essential for life. Even the energy in empty space seems to be tuned to perfection for intelligent life to arise. This idea of fine-tuning has given rise to different interpretations of the anthropic principle. One opinion suggests that the universe was designed on purpose with us in mind, possibly by a higher intelligence. Another idea, known as the principle of life, proposes that life is a natural part of the structure of the universe. However, these ideas are not widely accepted by the scientific community. Another way to see the anthropic principle is to say that the universe exists because we are here to observe it. A more practical view is that the universe seems perfectly suited for us simply because we live in a part of it that supports life. This could be due to the possibility that multiple universes exist, each with its own set of physical laws, ours being one of the few that can sustain life. The famous American writer Ursula Lewin once wrote, "The word must be heard in silence. There must be darkness to see the stars." This thought reflects the idea that everything in the universe has a beginning and an end. Some subatomic particles exist only fractions of a second. Some microorganisms live a few hours or days, and human beings live several decades. Even the stars end up going out after millions or billions of years. But what about the universe itself? Will it also come to an end? What will it be like, and what will happen after the universe dies? The oldest theory about the origin of the universe is called the steady-state theory. The defenders of this theory believe that the universe has no beginning or end, that it has always existed and will always exist in equilibrium. However, scientific discoveries ended up demonstrating that this theory is probably wrong, since irreversible processes occur in the universe. In the decades of 1910 and 1920, the Big Bang theory was developed and became widely accepted. Today, it is one of the most coherent scientific explanations for the origin and evolution of the universe. Many scientists contributed to the development of the theory of the Big Bang, with the work of Albert Einstein on the general theory of relativity as a basis. The main idea of this theory is that the destiny of the universe depends on dark energy, a mysterious force causing space to expand. However, we still do not fully understand dark energy, and there are many theories about it, each with its own strengths and weaknesses. According to current estimates, the universe is about 14 billion years old, based on the time elapsed since the Big Bang. The universe is in constant expansion and, depending on the behavior of dark energy, it will continue to expand forever at an increasing rate, or the expansion will slow down and, finally, be reversed. In the latter case, the universe could collapse again into an infinitely small point, similar to how it began. Science still does not know which of these possibilities will occur, but offers two possible scenarios: the Big Rip and the Big Crunch. The speed at which the universe expands is related to the distance between objects. The more separated they are, the faster they move from each other. Imagine a balloon that is inflated with air. If you put 2 points on the balloon and then inflate it, the points move away from each other. This is how the expansion of the universe works. It is space itself that is expanding. The more separated the points are, the faster they move away from one another. At a given moment, this expansion speed becomes faster than light speed. This point is known as the event horizon. Objects beyond this horizon disappear from view, moving beyond the reach even of the most advanced telescopes, never to be seen again. First, the most distant galaxies and clusters will disappear from the sky. Then, one by one, the stars of the Milky Way will fade, and finally, our own sun will go out and disappear. It is a somber vision of the future if the theory of the Big Rip turns out to be correct. The expansion of the universe will continue to accelerate, which would eventually cause the expansion forces to overcome the force of gravity. First, the clusters of galaxies would break apart and begin to disintegrate, followed by the galaxies themselves, and, next, the star clusters. Afterwards, even the stellar systems would disintegrate, since the stars would not be able to retain their planets and moons. Finally, matter would decompose into atoms, and these would decompose into subatomic particles. At that moment, matter as we know it would no longer exist. Beyond this, the physical laws that we know would no longer apply, and what would happen afterwards is impossible to predict. Current observations show that space is expanding and that the speed of this expansion is increasing. However, we do not fully understand the nature of dark energy, which could have unknown properties that could reverse the expansion. If that happened, the universe could begin contracting. This could happen if the gravitational attraction of all the matter in the universe became stronger than the expansion force. This scenario is known as the Big Crunch. In this case, the universe would continue shrinking until it was about 5 times smaller than it is now. The clusters of galaxies would merge into a massive supercluster that would fill the much smaller universe. Meanwhile, within the galaxies, events such as star formation, star death, and planet formation would continue as they do now. As the universe continues to contract, its volume would eventually be reduced to only 1% of what it is today, and all the galaxies would merge into one. By then, the temperature of the residual radiation would have risen to 274 Kelvin and would continue to rise. This increase in temperature means that there would be no liquid water left in the universe, which is essential for life as we know it. As the universe continues to contract and heat up, the planets will first burn and then melt, and all matter will collapse into a huge cloud of boiling plasma. Finally, even atoms and subatomic particles will disintegrate, and the universe will collapse into a singularity similar to how it was at its beginning. There's another theory related to the Big Crunch, known as the Big Bounce theory. According to this idea, after the universe collapses into a singularity after the Big Crunch, it could be reborn in a new Big Bang, beginning the cycle again. This process could be repeated indefinitely, to the extent that we can speak of eternity in a situation in which time and space no longer exist. Our understanding of dark energy is still too limited to say with certainty how long any of these scenarios might last. As far as we know, the next big rip or big crunch could occur while the stars and planets still exist, but what if it were not so? What would happen to the universe if its ultimate end was still very far into the future? The laws of physics suggest that the universe, as we know it, cannot last forever. Cosmology identifies 4 main eras, each associated with a specific phase of the universe. We are currently in the stellar era. During this time, there's a lot of interstellar gas that serves as raw material for the formation of new stars. New stars continue to form from this gas, but this process will eventually stop when all the interstellar gas has been exhausted. This era is expected to end sometime between 1 and 100 trillion years from now. By then, the Sun and most of the other stars will have burned their nuclear fuel and will have become white dwarfs, neutron stars, or black holes. We live in a world of 3 dimensions: up and down, left and right, forward and back. These are the directions in which we are able to move. Time is another dimension that we experience when moving from past to future. Together, these elements make up what we call spacetime in physics. Dimensions are like different directions in which you can move, like the lines on a graph. Normally, we only perceive 3 dimensions, but what if more exist? Regarding dimensions that we cannot see, theories like string theory and M theory suggest there could be additional ones. According to string theory, the smallest parts of our universe are not tiny points, but small vibrating loops of energy called strings. The mathematics behind string theory suggests that 10 or 11 dimensions must exist for everything to work. String theory tries to explain all the natural forces, such as gravity, electromagnetism, and the forces inside atoms, saying that everything is made of these strings. The way these strings vibrate determines the type of particle they become. So, why can't we perceive these additional dimensions? They could be incredibly small and folded, which would make them impossible to detect with our current tools. For example, imagine an ant walking on a rope. For the ant, the rope looks like a line because it cannot perceive its width. Similarly, these additional dimensions could exist, but be too small or hidden for us to perceive. If these higher dimensions are real, they could help us solve some big questions in physics, like why gravity is weaker than other forces. Perhaps gravity extends into these additional dimensions, which makes it appear weaker in our 3-dimensional world. These higher dimensions could help us better understand particles and forces, connect all the different forces in a complete picture, and lead to new technologies and a deeper understanding of the universe. Scientists are searching for evidence of these higher dimensions. One way is to study how gravity behaves at very small scales. If higher dimensions are real, they could cause slight differences in gravity that we could detect in laboratory experiments. Another method involves high-energy particle collisions, such as those at the Large Hadron Collider. In these experiments, particles collide at very high speeds. If any particle disappears into higher dimensions, it could be a clue that these dimensions exist. There are also other interesting ideas about higher dimensions. For example, some theories suggest that our universe could be a 3-dimensional brain floating in a space with more dimensions. In this brain world idea, our universe could be just one of many parallel universes, each of which exists as a separate brain in a space with additional dimensions. This raises exciting possibilities about how these universes could interact, such as through gravity or the exchange of particles. Another idea related to higher dimensions is the multiverse theory. This theory suggests that our universe is just a bubble in a vast space full of other universes, each of which exists in a higher dimension. These different universes could have their own physical rules and might even interact with each other. For example, If these universes collided, it could produce a massive explosion similar to the Big Bang that gave rise to our universe. Although the idea of higher dimensions is fascinating, it remains a theory. One of the biggest challenges is that these dimensions are not something we can see or measure directly at the moment. To detect them, we would need extremely high energy or very precise measurements beyond what we can do with current technology. Mathematics plays a key role in helping us explore the concept of higher dimensions. Many of the theories that suggest the existence of these additional dimensions are based on complex mathematics from areas like geometry, topology, and algebra. These branches of mathematics help us imagine and understand spaces that go beyond the three dimensions in which we usually think. Mathematicians and physicists collaborate to create models that predict how these higher dimensions could affect what we observe in the universe. Then they test these models with experiments and observations. Quantum mechanics, which studies how particles behave at very small scales, may also be influenced by higher dimensions. The strange and often puzzling behaviors we see in quantum mechanics could be due to interactions that take place in spaces with more than three dimensions. So, do higher dimensions actually exist in the universe? Although we do not yet have concrete evidence, the possibility of higher dimensions is an exciting area of research in theoretical physics. If these dimensions are real, they could change the way we view the universe and reveal new insights about the nature of reality. The Earth is rotating faster. Could this cause technological problems, and what do melting glaciers have to do with it? You may know that there are 86,400 seconds in a day, but in 2021 scientists discovered that the average day is 0.005 milliseconds shorter. This means that the Earth is rotating at a faster rate than usual. You might think, 0.005 milliseconds, what else matters? But this is surprising because it goes contrary to what we normally expect, since the Earth's rotation has been slowing down since it was formed in the distant past. The days on Earth were much shorter, but what does it mean that the Earth rotated faster? 3,500 million years ago, a day on Earth only lasted 12 hours. At that speed, life would have been chaotic, with an extreme climate and hurricanes ravaging the land. Faster rotation would have caused water to accumulate around the equator, flooding areas such as Indonesia and northern South America. That is the worst-case scenario, and it is unlikely that the Earth will rotate that fast again. If the Earth continues to accelerate, it could cause major problems. By 2030, we could face a major technological crisis. GPS depends on precise synchronization, and if a day becomes too short compared to the 24-hour standard, it could lead to serious problems. Satellites could lose their correct position in the sky, making them difficult to track. If we don't fix this in time, our navigation systems could become inaccurate and disrupt all our smart technology. Fortunately, there's a simple solution. The Guardians of Time can add or remove what are known as leap seconds to adjust for these small differences. They can modify the International Atomic Time to match with the Earth's rotation. By observing the night sky, we can monitor these small changes. This is how we know that the Earth is rotating faster, but that does not explain why, after millions of years of slowing down, the Earth is suddenly accelerating. So what's causing this? According to scientists, the melting of the polar ice caps is not only causing the rise in sea level, but also causing the Earth to rotate faster. When the Earth rotates faster, it creates more centrifugal force. Think of a figure skater. When she spins slowly with her arms outstretched and then brings them together, she starts spinning faster. This happens because she is bringing more mass closer to her spin center. A similar effect could be happening on Earth. Water has a special property. It expands when freezing. Glaciers, ice sheets, and ice-covered mountains are like gigantic blocks of frozen water. But what happens when they start to melt rapidly, as we are seeing now? When all that ice melts, the mass of the glaciers and ice sheets gets closer to the Earth's surface as the melted ice moves towards the center of the Earth's rotation, which makes the Earth rotate faster. This melted water is currently concentrated at the poles, so scientists believe that the Earth is rotating faster than usual. But will it continue to accelerate forever? Here is the complicated part. Scientists believe that this faster rotation is temporary. Although the Earth has been rotating faster in the last 2 years, experts believe that over time, it will slow down again and return to its long-term pattern. The reason for this slowdown has to do with the Moon. This is related to the gravitational relationship between the Earth and Moon. We only see one side of the Moon because it is in synchronous rotation with the Earth. As the Earth rotates, the Moon's gravity exerts a force on our oceans, creating tides. As the Earth rotates, the oceans move backward, causing a kind of oscillation in the Earth's movement. This interaction between the Earth and the Moon actually slows down the Earth's rotation over time. As the Earth's rotation slows down, and the lost energy is transferred to the Moon, causing the Moon to move further away from us. As the Moon moves away, its gravitational attraction on the Earth weakens, which will slow down the Earth's rotation in the long term. In addition, over time, the melted water from the polar regions could slow down the Earth's rotation even further. Some scientists think that this water will move towards the equator, slowing down the Earth even more. By the way, this process is called equatorial bulge. Imagine it as if the Earth is a larger spare tire around its center. This bulge already exists due to the centrifugal force of the Earth's rotation, but adding more water is not good. The additional water around the equator means that there is more mass further away from the center of rotation. The equatorial bulge will grow, leading to an even greater increase in the sea level around the equator than previously expected. This could cause hurricanes, typhoons, and cyclones that form near the equator because there is more water vapor in the air. So, although the increase in the intensity of the storms due to the Earth's rotation may be temporary, it is still a cause for concern, as more intense storms mean more natural disasters around the world. The origin of life on Earth is one of the greatest mysteries of science. While many theories suggest that life began here, on our planet, some scientists have proposed a fascinating alternative. That life, or at least the basic components of life, could have come from space. This idea, known as panspermia, suggests that the seeds of life could have been transported through the cosmos and finally taken root on Earth. But is there any evidence to support this theory? And if so, what does it mean for our understanding of life in the universe? Now, when talking about the fundamentals of panspermia, it is a theory that suggests that life or the ingredients necessary for life did not originate on Earth, but were brought here from outer space. The word panspermia comes from the Greek words pan, which means all, and sperma, which means seed. The idea is that life could be spread throughout the universe with small organisms or organic molecules traveling through space, and that could seed life on other planets, including Earth. Before discussing the evidence supporting panspermia, we first need to know several forms of panspermia. The first is something known as lithopanspermia. This theory suggests that life could have been transported to Earth on meteorites, comets, or other space debris. Microorganisms, or the basic components of life, could have adhered to these objects, surviving the harsh conditions of space. The second is known as radiophonic panspermia. This form of panspermia proposes that microscopic life forms, like bacteria, could be propelled through space by the radiation pressure of stars. These tiny organisms could travel great distances before landing on Earth. The third is directed panspermia. This is the most speculative form, which suggests that an advanced alien civilization could have intentionally seeded life on Earth or other planets. Although panspermia remains a hypothesis, scientists have discovered some evidence over the years. The first is meteorites containing organic molecules. Scientists have found organic molecules, including amino acids, the basic components of proteins, inside meteorites that landed on Earth. A famous example is the Murchison meteorite, which fell in Australia in 1969 and contained a variety of organic compounds, including amino acids, suggesting that these essential ingredients for life could be present throughout the universe. Another piece of evidence is extremophiles, which are basically microorganisms that we find on Earth, such as in deep-sea hydrothermal vents, acidic hot springs, and even in the vacuum of space, perhaps suggesting that life, or at least simple forms of life, could survive the journey through space and the conditions found on other planets. The third piece of evidence is the period of intense bombardment during the early years of the solar system, when Earth was bombarded by comets and asteroids, a period known as the late heavy bombardment. If these space rocks carried organic molecules or microorganisms, they could have deposited them on Earth, which could have started the process of life. But I recall a few years ago that news about life on Mars appeared on the front pages. Billions of years ago, Mars had conditions that could have harbored life. Evidence suggests Mars once had liquid water on its surface, a denser atmosphere, and a warmer climate than today. If life existed on Mars, it is possible that microbial life forms could have been ejected from the Martian surface by powerful asteroid or comet impacts. These impacts could have launched rocks containing microorganisms into space, some of which could have eventually reached Earth. This process of transferring life between planets through meteorites is a form of panspermia known as lithopanspermia. We also have evidence suggesting that Martian life could have been transported to Earth. The first is Martian meteorites found on Earth. We know that rocks from Mars reached Earth. Several meteorites found on Earth have been identified as coming from Mars based on their unique chemical and isotopic signatures. Impacts ejected these meteorites from Mars, and they traveled through space before landing on Earth. If these rocks contain microbial life, they could have seeded life on our planet at an early stage. Mars and early Earth had somewhat similar environments, with the presence of water, volcanic activity, and the potential for organic molecules. This similarity suggests that if life could begin on Earth, it could also have begun on Mars and then be transferred here. So, if life can spread through space, this suggests that life could be common throughout the universe. Planets, moons, or even asteroids capable of harboring life could have been seeded by microorganisms or organic molecules from other places. Although the possibility of life coming from other places is exciting, many scientists still believe that life began on Earth itself through a process known as abiogenesis. This theory proposes that life arose naturally from non-living matter, such as simple organic compounds. This process would have occurred over millions of years. There's also some evidence suggesting the existence of natural primitive life on Earth. The first is the Miller-Urey experiment in 1953. Scientists Stanley Miller and Harold Urey conducted an experiment that simulated the conditions of early Earth. They discovered that by applying an electrical charge to a mixture of water, methane, ammonia, and hydrogen, they could produce amino acids, the basic components of proteins. This experiment provided strong evidence that the basic components of life could have formed naturally on early Earth. Another strong piece of evidence is hydrothermal vents. Some scientists believe that life may have originated around hydrothermal vents on the ocean floor. These vents release heat and chemicals from the depths of Earth, creating an environment that could have favored the formation of complex organic molecules. Music, the extremophiles found today around these sources, offer clues that similar conditions could have given rise to primitive life. Another theory suggests that life could have originated on the surface of minerals, particularly clay. Certain types of clay can attract and concentrate organic molecules, potentially providing a surface where complex chemical reactions could occur. The question of whether life on Earth came from space is fascinating and continues to puzzle scientists. While the panspermia hypothesis offers a tempting possibility, it remains only a possibility. The evidence we have is compelling, but not conclusive. Most scientists still believe that life began on Earth through natural processes, although the idea that life could be spread throughout the universe and be able to travel through the cosmos is exciting. The Moon is one of the largest natural satellites in our solar system, almost as large as Mercury. This similarity in size raises an interesting question. How were the Earth and the Moon formed this way? Why do these two bodies orbit each other? There are some fascinating facts about the Earth and the Moon. For example, a space probe orbiting Mars took a photo showing the Earth and Moon from Mars' perspective. An interesting fact about the Moon is that it has very little iron in its core, unlike Earth, which has a lot of iron in its core, giving a magnetic field. This difference is confusing because if the moon formed in the same region as Earth, why does Earth have so much iron in its core while the moon has so little? Another curious aspect is the amount of spin within the Earth-Moon system. The moon orbits the Earth quickly, and both the Earth and moon spin. In physics, spin or angular momentum does not appear out of nowhere. They have to come from somewhere. So when we see the Earth and the moon spinning quickly and the moon orbiting quickly around the Earth, there must be an explanation for it. Why is there so much spin within the Earth-Moon system? One of the greatest achievements in the history of humanity was when we landed on the moon in 1969. During this mission, we gathered lunar rocks and brought them back to Earth. Scientists discovered that these lunar rocks are very similar in composition to the rocks of the Earth, which suggests that the moon and the Earth could come from the same source. By studying the disintegration of radioactive elements in lunar rocks, scientists could determine their age. These rocks appear to be between 30 and 50 million years younger than Earth. While this difference may not seem significant, since the Earth is about 45 billion years old, it indicates that the moon formed a little later than the Earth. Another interesting fact has to do with isotopes, which are different forms of a single element. For example, carbon-12 has 6 protons and 6 neutrons, while carbon-14 has 6 protons and 8 neutrons. The same concept applies to oxygen. The proportion of these different forms of oxygen can be measured precisely in various parts of the solar system. These proportions vary depending on how close or far a planet formed from the Sun. However, on Earth and the Moon, these proportions are very similar, indicating a common origin. So we have a little mystery here. The Moon is slightly younger than Earth, spins quickly, is made of similar materials, but has very little iron. What is the explanation for this? There's a widely accepted theory that explains all these things. Some people question it, which shows how science works. It is not 100% proven or accepted, but it makes sense based on evidence. Scientists have several theories about how Earth and the Moon formed. One of the most accepted is the giant impact hypothesis. The most accepted theory suggests that about 50 million years after Earth formed, another planet the size of Mars came very close to Earth and collided with it, hitting it at an angle and releasing a lot of debris without reaching Earth's core, since heavy elements like iron sank toward the center when the planet formed. Most of Earth's iron was already in its core, so the material that came off had very little iron. This collision also caused great spin, similar to when a soccer ball is kicked on one side and spins and curves. This explains why the Earth-Moon system has so much spin. The Moon formed from the debris of this collision, so it is composed of materials and isotopes similar to Earth's. Since the collision occurred 50 million years after the formation of the Earth, it also explains why the rocks of the Moon are slightly younger than those of the Earth. It seems that the Moon formed from a planetary collision about 45 billion years ago. All the evidence supports this idea, especially the 4 key observations about Earth and the Moon, in addition to the fact that when we went to the Moon and collected samples, the laboratory analyses further supported the theory. This collision not only formed the Moon, but also played an important role in shaping Earth's future. The impact likely tilted Earth's axis, so we have seasons. Without this inclination, our planet might not have the weather patterns that support diverse life forms. The Moon also helps stabilize Earth's rotation, preventing extreme inclinations over long periods, which would have drastic effects on our environment. In addition, the gravitational interaction between Earth and the Moon creates the tides, which have influenced the evolution of life on Earth. The regular rise and fall of sea level has affected coastal ecosystems and human activities for millennia. Interestingly, the Moon is gradually moving away from Earth. Measurements show that the Moon moves about 38 centimeters away from Earth each year. This slow separation affects Earth's rotation and the length of our days. Millions of years ago, the days were shorter, and as the Moon continues to move away, the days on Earth will gradually lengthen. Although the giant impact hypothesis is the most accepted theory, there are other interesting theories. One of them is the fission theory, which suggests that the Moon was once part of Earth and separated due to its rapid rotation in its early days. However, This theory has difficulties explaining the moon's current orbit and how such a separation could have occurred. Another theory is the capture theory. According to this idea, the moon formed elsewhere in the solar system and was later captured by Earth's gravity. This could explain why the moon has a different composition than Earth. However, capturing such a large body without it breaking or escaping again seems very unlikely. Despite these theories, the exact process of the moon's formation remains a topic of scientific research and debate. The unique relationship between Earth and the moon has a significant impact on life here. The moon's gravitational pull creates the tides, which have influenced the evolution of life and the development of civilizations. The regular rise and fall of sea level has affected coastal ecosystems and human activities for millennia. The Earth-Moon system is a fascinating topic of study that provides information about the formation and evolution of planetary bodies. The differences in composition, shared angular momentum, and the ongoing relationship between Earth and its only natural satellite tell a complex and intriguing story about our place in the cosmos. Uranus, the seventh planet from the Sun, is a unique world in our solar system. One of its most unusual characteristics is its extreme axial tilt. Unlike most of the planets, which rotate with their axis more or less straight up and down, Urano is inclined at an angle of approximately 98 degrees, which means that Urano basically rolls around the Sun on its side, with its poles facing the Sun and turns directly. Let's explore the details of this strange tilt and the mystery that surrounds it. It is believed that the inclination of Urano is the result of a massive impact that occurred billions of years ago, shortly after the planet formed. According to this theory, a huge object, possibly as big as Earth or bigger, collided with Uranus, causing it to overturn on its side. This traumatic event probably changed the rotation and orbit, causing the extreme tilt that we observe today. Although this theory is widely accepted, the exact details of the impact and the object that caused it remain unknown. Some scientists suggest that it was not a single large impact, but a series of smaller collisions that gradually tilted Uranus to its current angle. These smaller impacts could have slowly changed the planet's axis without destroying it or drastically altering its general structure. The extreme inclination of Urano has a great effect on the seasons and the climate of the planet. On Earth, we experience relatively mild seasonal changes because our planet's tilt is only about 235 degrees, but with a 98 degrees tilt, the poles of Uranus each receive about 42 years of continuous sunlight, followed by 42 years of darkness, since Uranus takes 84 Earth years to complete an orbit around the Sun. This creates some of the most extreme seasonal variations in the solar system. During its long summer, a pole of Uranus remains under continuous sunlight, while the opposite side remains in darkness. As Uranus continues its orbit, this gradually reverses and the opposite pole experiences summer. This unique tilt leads to extreme temperature changes and unusual weather patterns. The planet's atmosphere, composed mainly of hydrogen, helium, and methane, shows dynamic and complex behavior due to these extreme seasonal changes. The atmosphere of Uranus is another fascinating characteristic of the planet. Its greenish-blue color comes from the methane in the atmosphere, which absorbs red light and reflects blue and green light, giving Uranus its distinctive tone. The atmosphere also has incredibly fast winds that can reach speeds of up to 560 miles per hour. These winds, combined with the planet's extreme tilt, create a turbulent climate and dramatic cloud formations. One of the most interesting aspects of the atmosphere of Uranus is the presence of dark spots similar to the Great Red Spot of Jupiter. These dark spots are believed to be vortices or deposits, and their appearance may change over time. The observations of the Hubble Space Telescope and other instruments have helped scientists to study these characteristics, offering valuable information about the dynamics of the atmosphere of Urano. The unusual tilt of Uranus also affects its magnetic field. Unlike Earth, where the magnetic field is approximately aligned with the axis of rotation, the magnetic field of Uranus is tilted about 59 degrees with respect to its axis. This means that the magnetic field is off-center and is more complex than that of the Earth. Scientists believe that the magnetic field of Uranus is generated by a layer of ionic mud inside the planet, composed of water, ammonia, and methane. This layer, combined with the rotation of the planet, creates the unusual magnetic field of Urano. The study of the magnetic field of Urano provides scientists with important clues about the internal structure of the planet. They believe that Uranus has a core composed of rock and metal surrounded by a thick layer of icy materials. The outermost layer is formed by gaseous hydrogen and helium, similar to Jupiter and Saturn. Understanding the magnetic field helps researchers create models of Uranus's interior and its formation history. In addition to its tilt and magnetic field, Uranus has a system of rings and moons that make it unique. The rings of Uranus were discovered in 1977 and are much darker and narrower than those of Saturn. These rings are formed mainly by large particles and are believed to be relatively young, possibly formed from fragments of shattered moons or captured objects. Uranus has 27 known moons, the largest being Titania, Oberon, Umbriel, Ariel, and Miranda. These moons are named after characters from the works of William Shakespeare and Alexander Pope. Each moon has its own unique characteristics and geology. For example, Miranda, the innermost of the large moons, has a very diverse surface with deep canyons, ridges, and areas that appear to have been remodeled by geological processes. This diversity suggests a complex history of internal activity and resurfacing. The unique characteristics of Uranus have made it a topic of great interest to planetary scientists. Despite its fascinating characteristics, Uranus has been relatively little explored. The only spacecraft that visited Uranus was Voyager 2, which flew by the planet in 1986. Voyager 2 provided valuable data and images, but there is still much to learn about this distant world. There is also a hypothesis that suggests the influence of a large moon or multiple moons that could have exerted gravitational forces strong enough to tilt Uranus. However, the current moons of Uranus are relatively small compared to the planet, which makes the giant impact hypothesis more likely. The study of Uranus also helps us better understand the solar system as a whole, since by learning more about Uranus, scientists can obtain information about how planets form and evolve. Uranus is considered an ice giant because it has more icy materials compared to the gas giants Jupiter and Saturn. The study of ice giants like Uranus and Neptune can help researchers understand the different types of planets and the conditions that lead to their formation. In recent years, there has been growing interest in sending a dedicated mission to Uranus. Said mission could include an orbiter and possibly a probe to study the planet's atmosphere in detail through long-term observations. Scientists could monitor seasonal changes, atmospheric dynamics, and variations in the magnetic field. In addition, close-up studies of the rings and moons of Uranus could provide new insights into their composition and history. In 1950, a famous physicist, Enrico Fermi, asked a simple but important question during a lunch with his colleagues. If our galaxy is so big, where are all the advanced alien civilizations? This question is now known as Fermi's paradox. The paradox comes from the fact that, with around 400 billion stars in our galaxy, it seems likely that some planets must have intelligent life. If that is true, these civilizations would have had plenty of time to explore and perhaps even visit Earth, but we have not found any clear evidence that this has happened. To explain why we have not seen any sign of extraterrestrial civilizations, despite the high probability that they exist, several theories have been proposed. The first is that traveling between solar systems could be extremely expensive and require enormous amounts of resources. For example, sending a spacecraft even to the nearest star would require an enormous amount of energy and money, which would make it impractical. Another is limited expansion, according to which, even if a civilization begins to explore and colonize other planets, it could be difficult to continue expanding over the generations, since the effort needed to continue moving from one star system to another could be too difficult to maintain. Another idea suggests that it is possible that the galaxy is full of activity in other areas, but that we are in a quiet part where not much happens. Or a natural reserve where aliens observe us from a distance, to make sure we don't know they exist. To understand where Fermi's paradox comes from, we have to look at two key ideas. The first is the Drake equation, created by Frank Drake, an important figure in the search for extraterrestrial life. This equation suggests that there could be thousands of civilizations in our galaxy that are capable of sending us signals. The second idea is Fermi's paradox, which asks why we have not found any clear sign of intelligent extraterrestrials, such as evidence of space travel between stars. The name of Fermi's paradox is a bit misleading, since it was given in honor of Enrico Fermi, but he did not actually create this theory. Even so, the idea is important when debating the possibility of extraterrestrial life and has influenced research funding. For example, Fermi's paradox influenced Senator William Proxmire's decision to stop funding NASA's SETI program in 1981. Although Carl Sagan managed to reactivate the program briefly, it was closed again in 1993 by Senator Richard Bryan. However, the search for extraterrestrial life has not stopped. Although NASA does not fund SETI as it used to, research continues through other sources. The SETI Institute, a private nonprofit organization, carries out the work. The institute collaborates with universities, companies, and even government agencies, including NASA, to continue searching for signs of extraterrestrial life. Interestingly, the term Fermi paradox does not actually come from Fermi himself. What we know of his thoughts comes from a lunch in Los Alamos in 1950, as recalled by physicist Eric Jones, who interviewed 3 of Fermi's colleagues during this lunch. Fermi wondered about space travel. This conversation ended up leading to what we know today as Fermi's paradox. According to Teller and York, Fermi was more interested in whether it was possible to travel between stars than in whether aliens existed. Fermi's paradox is usually understood in the sense that there is no evidence of extraterrestrial life, but this was not something firm. His main concerns focused more on whether space travel was possible, which made sense in 1950, when rockets could not even reach orbit, let alone other planets or stars. The idea that the absence of aliens on Earth means that there are no aliens anywhere was first introduced by astronomer Michael Hart in 1975, not by Fermi. Michael Hart argued that, if intelligent aliens existed, they should have already colonized the Milky Way, since we have not seen any evidence of them on Earth. He suggested that humans might be the only intelligent beings in our galaxy. He even thought that looking for alien civilizations could be a waste of resources. However, many people disagree with his conclusion. They point out that space travel could be impossible, that aliens might choose not to colonize other planets, or that they might have visited Earth long before humans existed without leaving a trace. Despite these criticisms, Hart's idea is still widely discussed when talking about extraterrestrial life. In 1980, physicist Frank Tipler expanded on Hart's ideas by considering the enormous resources needed to explore billions of stars. Tipler suggested the idea of self-replicating robots with human-like intelligence. These robots could be sent to a nearby star, use local resources to create copies of themselves, and those copies could continue to spread throughout the galaxy. Tipler concluded that, since we have not found any of these advanced robots on Earth, it could mean that we are the only intelligent civilization, not only in the Milky Way, but in the entire universe. This idea is bold, based solely on the fact that we have not yet found aliens. What we now call Fermi's paradox comes mostly from the ideas of Hart and Tipler, but over time their theories have mixed with Fermi's original question, leading to some confusion about the real origin of the paradox. This confusion probably began in 1977, when physicist David Stevenson used the term Fermi paradox in a publication in which he presented Hart's theory as an answer to Fermi's question. A more accurate name for this idea might be the Hart-Tipler argument against the existence of technological aliens, although this name is not as catchy as the erroneously attributed Fermi paradox, but it would better recognize the true creators of the concept. The search for extraterrestrial life remains a topic of great interest to scientists. The James Webb Space Telescope is providing us with incredible new images and data, while the Mars rovers are studying the planet up close. There are also plans for future missions to explore the farthest parts of our solar system. The question of whether we are alone in the universe remains unanswered, and until we discover otherwise, the search for extraterrestrial life will continue to be a priority for humanity. Scientists have developed different ways to search for life beyond Earth. The key research area is the study of exoplanets, which are planets orbiting stars outside our solar system. The Kepler Space Telescope and other missions have discovered thousands of exoplanets. Some are in the habitable zone, where conditions could allow life. The habitable zone is the region around a star where temperatures could allow liquid water to exist, since liquid water is essential for life as we know it. These exoplanets are the main candidates to continue studying the existence of life. For life to exist, certain ingredients are needed in addition to liquid water. Life requires key elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements are the basic components of the organic molecules that make up all known forms of life. Interestingly, these elements are common in the universe. They have been found in interstellar clouds, comets, and even on other planets and moons of our solar system. Scientists are also looking for biosignatures, which are signs of life that can be detected from afar. Biosignatures can include specific gases in the atmosphere of a planet, such as oxygen or methane, which could indicate the presence of vital processes. Another interesting research area is the search for technosignatures, signs of advanced civilizations. This includes the search for radio signals, laser pulses, or other types of technology that could suggest intelligent life. Projects like SETI have been scanning the skies for decades, hoping to capture a signal from an alien civilization. While searching for life outside Earth, scientists are also exploring the possibility of life within our solar system. Moons like Europa and Enceladus, which have oceans under their icy surfaces, are especially interesting. These oceans could have the right conditions for life, protected from space by a thick ice layer. As technology improves, our ability to search for extraterrestrial life will continue improving. New telescopes, space missions, and artificial intelligence will increase our chances of detecting and studying possible signs of life. We have found more than 4,000 planets orbiting other stars, and we now know that almost every star has at least one planet. Approximately one of these stars has Earth-sized planets orbiting it. With around 100 billion stars in the Milky Way, there are likely billions of Earth-sized planets out there. It seems unlikely that only one of these planets has life, given the enormous number of Earth-like planets in our Milky Way alone. We have to ask ourselves, are we really alone in this galaxy? The Hubble Space Telescope has shown us about 100 billion galaxies. Each has about 100 billion stars. In total, that's about 10,000 trillion stars in the visible universe, a number difficult to imagine given how large the universe is. The chances of life existing elsewhere seem quite high. Think about how vast our universe is, full of an enormous number of stars. Even in our own Milky Way, with its 100 to 400 billion stars, it seems unlikely that Earth is the only place with intelligent life. The enormous number of stars suggests that life elsewhere in the universe is almost certain. Frank Drake was a scientist who tried to figure out how many detectable civilizations might exist in our galaxy. He came up with a series of questions that, when combined, give us an estimate. This set of questions became known as the Drake equation, which helps predict the number of detectable civilizations in the Milky Way. For more than 60 years, the Drake equation has been our main tool for estimating how many civilizations might be out there, with figures ranging from 1,000 to 100 million planets that harbor civilizations. In the Drake equation, R is the rate at which new stars form in our galaxy each year. Next is the percentage of these stars that have planets. Then we look at NA, which estimates how many of these planets are in the habitable zone where life could exist. This remains largely unknown as we don't know much about planets beyond our solar system. The number for all tries to figure out how many of these planets actually have life. Then, Phi estimates how many of those planets develop intelligent life. When Frank Drake created his equation, he focused on radio astronomy. He wanted to know what the probability was that alien civilizations were sending signals that we could capture with our technology, which is represented by the variable phi in his equation. In the 1960s, many scientists believed radio waves were the most likely way advanced aliens would communicate. Earth has been sending radio signals into space for almost 100 years, reaching stars within an 80 light-year radius. But there is still a big question. Would aliens elsewhere in the universe still use radio waves, or would they consider them obsolete, like we consider smoke signals? In the last part of the Drake equation, he tries to estimate how long a civilization could be detectable in our galaxy. Frank Drake, the scientist behind this equation, was concerned that even if a society developed advanced technology, its signals would only last a short time. So even if civilizations lasted thousands of years, we could only capture a brief signal from them. When Drake first made his calculations in 1961, he estimated that there could be 4 to 10 detectable civilizations in our galaxy. But with today's scientific updates, the number is much lower. The new estimate of N, the number of detectable civilizations, is approximately 0.127. This means that in every 100,000 years of our galaxy's history, only about 127 civilizations could become detectable. Drake's original belief that there could be around 10,000 civilizations in the Milky Way suggests a very busy galaxy, but the difficulty of finding even one civilization among 100 million stars demonstrates how difficult it is to make real claims about how common or rare these civilizations are. Astronomers may need to study 10 million stars, demonstrating the enormous effort required. We still do not know how many alien civilizations could exist out there. Estimates range from a few to up to 100 million in the Milky Way alone, but some think we might be the only advanced civilization in our galaxy. That does not mean we are alone in the entire universe, which is incredibly vast. The observable universe extends to about 92,000 million light-years and has between 100,000 million and a trillion galaxies, each with around 100,000 million stars. So there's a good chance that intelligent life exists somewhere, although perhaps not in our Milky Way. Throughout the history of Earth, there have been more than 10,000 million species, but none has shown the intelligence, curiosity, and ability to create complex tools like humans. Even intelligent animals, such as whales and dolphins, do not seem to think deeply or manufacture complex tools. Humans have only existed for a few hundred years, so for most of Earth's history, an alien looking at our planet would not see any advanced technology or signs of superior intelligence. Nor is it clear if being so intelligent is good for us in the long term, since, while our intelligence has improved the lives of many, it has also brought us closer to self-destruction. Recently, astronomers have been trying to get better estimates of how many alien civilizations there could be in our galaxy. They focus on 2 big questions. How likely is it that life begins on planets similar to Earth from inert materials? And what are the chances that this life becomes intelligent? Even with these estimates, there is still much disagreement. Some scientists argue that with so many Earth-like planets, we cannot be the only ones. Others want solid evidence and wonder if there are so many civilizations out there. Why have we not found any evidence of them? This is the big question behind what is known as the Fermi paradox. If extraterrestrial life is common, where is everyone? The search for extraterrestrial intelligence has been actively scanning the sky, but we have only looked a few hundred light years away, which is only a small part of our galaxy. If the galaxy were full of life, especially advanced life, some of it would be much more developed than us. The stars in our galaxy went through processes billions of years ago that created the elements necessary for Earth-like planets. So there could be civilizations out there that are billions of years more advanced than us, considering how quickly human technology has developed in just a few hundred years. Imagine what a civilization could achieve in thousands or even millions of years. Such civilizations could potentially travel between stars and colonize the galaxy. In theory, they could fill the entire galaxy in just a few million years. If they existed, we might expect them to have reached us already. On the night of July 15th, 1977, astronomer Jerry Amon, a volunteer in the search for extraterrestrial life, was scanning radio signals when something surprising happened. He captured a strong and unusual signal. This signal lasted 72 seconds, was 30 times stronger than the usual background noise, and appeared to come from the direction of the constellation Sagittarius. Music. The data was translated by a computer into a series of letters and numbers, resulting in the sequence 6 EQJ5. When Jerry saw the impression the next day, he was so amazed that he circled the sequence and wrote, "Wow," next to it. That is how the signal got its name. Signal experts signal. Experts concluded that the source of the signal was emitted in an R-shaped pattern, like the rotating beam of a lighthouse. It is as if we only capture the signal when it is directed directly towards us and then lose it when it moves away. Despite all the monitoring and analysis done since then, the WOW signal remains one of the strongest pieces of evidence, and its origin is still widely debated and investigated. Whether it is really a message from aliens or not remains a mystery. Scientists believe that what we detected as the WOW signal may not have been the entire transmission, but part of a repetitive signal. To understand why we do not capture everything, we have to see how the telescope worked. The WOW signal was captured by the Big Ear Telescope of The Ohio State University, built specifically to search for extraterrestrial signals. The telescope was huge, the size of 3 football fields, with a large mirror that captured the signals and reflected them towards smaller mirrors. These mirrors, in turn, directed the signals to 2 receivers for analysis. However, the way the Big Ear Telescope was built made it difficult to capture the signal consistently after first detecting the WOW signal. There was a delay of a few minutes before the second receiver could check the same area of space, and by then, the signal had already disappeared. This interval in detection is a major obstacle when confirming where the signal came from. The design and operation of the Big Ear Telescope show how the structure of this type of equipment can affect our ability to confirm signals. If the telescope had been able to monitor the same point continuously or revisit it quickly, scientists could have seen more signals from the same region in the constellation Sagittarius. This could have provided clear evidence of where the signal came from. The limitation here shows how important the design of the telescope is when it comes to searching for signals from other civilizations. The Big Ear was not like traditional telescopes that use mirrors to capture light, but was a radio telescope that used parabolic wire antennas to detect radio frequencies that are invisible to our eyes. Unlike modern telescopes, which can rotate in all directions to scan the sky, Big Ear could only tilt its reflector up and down, limiting it to observing a narrow strip of the sky at a time. This design was chosen because it was simpler and cheaper to build than other more advanced systems. To overcome this limitation, the designers found an ingenious way to increase its range by taking advantage of it to move the telescope to the left and to the right and adjusting the reflector to cover different angles. Big Ear was finally able to observe any point in the sky. This use of the Earth's natural movement was a clever way to make the most of the telescope's limited mobility, allowing it to cover more ground despite its restrictions. But there was still a drawback. Since the telescope depended on the Earth's rotation, it could not follow the same point in the sky for long. This means that it could have lost additional signals coming from that region. Imagine an entire orchestra of signals sent from that point after the WOW signal, but Big Ear only captured a brief note of what could have been a much larger broadcast. The challenges faced by SETI in its search for extraterrestrial life are largely due to the immensity of space and limited resources. They cannot dedicate a single telescope to observing a point for years, hoping to obtain an answer. Instead, they scan large areas of the sky, moving from place to place to increase their chances of capturing a signal, even if only for a moment. This approach is like throwing a wide net in different places instead of waiting at one single point. It is a practical strategy, given the uncertainty of where and when a signal might appear. The search for extraterrestrial signals is not entirely random, although it may seem so. Unlike fish, which can be attracted or scared away by our actions, extraterrestrial signals are not influenced by our attempts to locate them. Although sweeping the sky with a telescope may seem like a guessing game, it is the best approach, taking into account the immensity of space and the uncertainty of where signals may be. However, this approach has its challenges, especially when following up on strange signals like the WOW signal. Over the years, radio telescopes have captured several mysterious, short-lived signals similar to the WOW signal, rapid bursts of radio waves that we still do not fully understand. The main problem is that, without continuous observation and dedicated studies, these signals remain mysterious and often go unnoticed. Without proper monitoring, we can miss important data, which leaves us only with guesses about these signals' origin. This raises an important question. The reason we have not found signals of intelligent extraterrestrial life could be due to how we are looking for it. Of course, this is just one possible explanation. In this debate, we have addressed some of the technical challenges posed by the detection of extraterrestrial life, but there are also many other more speculative theories that address deeper questions about our place in the universe and the nature of other civilizations. These theories open interesting possibilities about what life beyond Earth could be like. The question of whether aliens are watching us from the stars is both exciting and complicated. The large number of stars and galaxies in the universe suggests that the conditions for life, including intelligent life, could be common far beyond Earth. If only a small percentage of the planets that surround these stars can harbor life, then life could be widespread throughout the cosmos. There are many reasons why we have not yet established contact with other civilizations. One reason could be the great distance between stars, which makes communication and space travel extremely difficult. Another reason could be the timing of when civilizations arise, which may appear and disappear at different times, missing the chance to connect. Another important factor is the way communication happens. Advanced civilizations could use technologies or methods that we still do not understand or cannot detect. It is also possible that they choose not to contact us, perhaps observing us from afar, as we study less developed species on Earth.